Hello everyone. In this video, we are going to solve another kinetics of rigid bodies problem in 2D, the planar problems. What we have here is a 4-bar linkage A, B, C, D, where the output member CD has an overhang that goes all the way to E, right? And the input member AB rotates at a constant omega of 10 radians per second. Counterclockwise means the alpha of this member is 0. The masses for members BC and CD, which can be modeled as a slender bar, are 2 and 3.6 kilograms, and their length are also given. At this moment, you want to determine the forces applied to pin B and pin C, okay? So, or exerted on member BC by pin B and pin C. So, basically, we need to find BX, BY, CX, and CY. So what we need is to draw the free body diagrams of the two members BC and CDE. You might say, what about AB? Well, we can draw that one as well, but we don't have all the information for it. The mass of it is not given. The torque at pin A that causes the member to rotate is not given. So if we draw it for member AB, it's not going to give us the information that we need. So these two FBDs of BC and CDE should be enough. So here, this is point B, this is point C. I call the center of this one point G or G1. And then I have point C here, and then the pinpoint D, and the endpoint E, and the centroid here at the center, I can call it G2. So G1 and G2 are the centroids for these two members. Good. What forces do we have? Definitely at the centroids, we have the masses. So this is like mass of BC, which is 2 kilogram. So I write it as 2 times G. This is the mass of CDE, which is 3.6 times G, because the mass of the member is 3.6. Then we have pin reactions at B and C. So at B we have 2 pin reactions, BX and BY. Similarly, here we have CX and CY. And then for member CDE on pin C, we have the reaction to those two C's. So it's going to be the same CX but backwards and the same CY but backwards. And then at D, we also have 2 pin reactions. So we have dy and dx. So here are these 6 reactions, and we use the traditional xyz coordinate as the problem is suggesting. I would call these FBDs FBD number 1 and FBD number 2. So I can refer to them. So for FBD number 1, I write down the equations of motion. You know, we have 3 equations in the XY plane for a rigid body. So we have sum of the forces along the x direction is going to be Bx plus Cx is equal to mass, which is 2 kilogram, times acceleration of the centroid G1 along x direction. Sum of the forces along y is equal to By plus cy minus mg, m is 2, is equal to m times acceleration of point g1 along the y direction, and then summation of the moments about g1 in a counterclockwise positive manner. Why? Because z is counterclockwise here, rotation z. That is going to be, if you look here, the moments of bx, by are both clockwise, and cx and cy are both counterclockwise. So it's going to be negative bx times the distance from bx to g1, which is this distance here. And if we look at it, it's going to be, since point g1 is in the middle, it's going to be half of that 400, so it's going to be 200. And if I write it in meters, it's going to be 0.2. by is similar, negative by. The distance for by is this distance. And if you see, that is going to be half of this 700, so it's going to be 350. Write it in meters, 0.35. And then similarly for cx and cy, we have similar arms, but they are both positive. So it's going to be positive cx times 0.2. Then positive cy times 0.35. This whole thing is equal to I about point G1 times alpha of member BC, right? So these are my, let's see if I can clean this up without cleaning the rest of it. Yeah, it's not too bad. So if I call these equations 1 to 3, then I need to look at FBD number 2. And again, I have summation of the forces along x. It's going to be dx minus cx. And this is equal to mass of that object, 3.6, times acceleration of point g2 along x direction. Summation of forces in the y equals dy minus cy minus 3.6 times g is equal to 3.6 times acceleration g2 along the y direction, and then summation of the moments about g2 in a counterclockwise positive manner is equal to, so I can do that. I can also, if you want, I can also, instead of taking moment about g2, I can also write the equation about point D, because D is a permanently fixed point. So I can say sum of the moment about D equals I about D times alpha, right? So I can write this equation about the fixed point that way as well. What's the advantage? The advantage is this dy unknown that is passing through D is not going to show up in the left side. While if I do it about G, dy and cy both show up. So it's a better idea to write your moments equation about point D instead of the centroid here. And you can do that because it is a permanently fixed point, okay? So let's go ahead and do that instead. So I will change that to point D. Now about point D, we have two forces. One of them is the unknown cy, which has a counterclockwise moment. The distance between cy and D is definitely 400. So it is going to be cy times 400 in millimeters, or 0.4 in meters, minus the mg force, 3.6 g, right? That force also has a moment about D that's definitely clockwise negative, and the distance between this g force, this mg force, and D, right? So this is g2 in the middle, and this distance here is clearly 150, right? because the distance between G2 and C is half of the whole length, right? This distance, the whole length is 1100, 400 plus 7. So this distance is half of that, 550. 400 of it is to D, the remaining is 150. And so this is going to be times 150. And that is equal to I about point G2 time, or D, remember we have to write it about D, times alpha of member CD. Okay, so you have to do I about D. So this is 4, this is 5, this is 6. I about D, I can use parallel axis theorem and say this is I about G1 plus the whole mass of the block, which is 3.6, times the distance between D and G, which we found it is 150 squared. So here I'm using the parallel axis theorem, and I can find I about D. There we go. So here are my 6 equations. Now the question is, how many unknowns do I have, right? Clearly the unknowns of interest, bx, cx, by, and cy are showing up in my equations, but I have a bunch of more unknowns that I need to figure out. So what are the unknowns? As I said, bx and cx, by and cy, dx and dy, then the accelerations at the centroid G1 and G2, and then the alphas. So you have 12 unknowns, but 6 equations. There is no way you can solve for any of your unknowns, especially because all of your equations have more than 2 unknowns, and if you look at any subset of them, still, in any subset you look, you have more unknowns than equations. So the only way to do it is to find these A's and alphas first through kinematics, using the velocity and acceleration analysis for this 4-bar linkage A, B, C, D. Then once you come back, then you have 6 equations and 6 unknowns. All of them are forces. So before you can do kinetics analysis and find the forces, you need to find the accelerations, find A's and alphas. And before you can do A's and alphas, as you know from my previous videos, you first need to find omegas of the members. If you don't know the omega of each member, you cannot do acceleration analysis. Omega of AB is given, but not omega of CD and BC. You have to find them first. So first do, you see, that's the process. You first do the velocity analysis and find the omegas, right? And if there are V relatives for sliding contacts, then you go and do acceleration analysis. To find alphas and A's at the centroids. And once you have those, now you can find all of the forces and the couples. So this is going to be kinetics analysis. Where you can find forces and torques or moments. Okay, so that's the process. Here we started at the very end. We started with these equations 1 to 6. So we have these previous steps missing. So if I want to go back and get my A's, then it asks me to first go and find omega. So instead of me starting in the middle, I go back and start from here. First find omegas, then find alphas, and then I come back, and now there will be enough equations for me. So what I need is to look at the acceleration and velocity analysis for this guy, and for that reason, I'll do it on another page. So this is my mechanism. Omega AB is 10 radians per second constant. counterclockwise, which means my alpha AB is 0. First, I find omega BC and omega CD, and then I can find alpha BC and alpha CD, and then I can find A at point G1 and A at point G2 that I need. And again, G1 was this point here, and G2 is this point here. Okay, so this is the kinematics analysis of this mechanism. So first, let's do omegas. So since I have motion at member AB, I start at member AB and I say V of B equals V of A plus omega AB cross R of B with respect to A. And I replace V of A is 0. Omega AB is going to be positive 10K. And R of B with respect to A, which is this vector going from A to B, this vector, that is 400 upward, so it's going to be 0.4J. And you carry out the cross product, you will get a negative 4I meters per second. Now that I know V of B, I go to the next member that shares points B. So it's BC, so I go from V of B to V of C. Say V of C equals V of B plus omega BC cross R of C with respect to B, where V of B is already known. That's this number. Omega BC I don't know, I just assume it's positive K. It could be negative K, that's okay, but it is along Z. R of C with respect to B is this vector going from B to C. And clearly you need to go 400 down and 700 forward, so it is going to be 0.7I and minus 0.4J. And here I have no information about V of C through member BC. Okay, it has two components. I don't know anything. And if I have two unknown components for V of C and one unknown omega BC, this vector equation gives me two scalar equations, but I have three unknowns and I cannot solve. So the only way I can work on this is to say C also belongs to member CD. So I can find velocity of C also through member CD and say this is equal to V of D plus omega CD cross R of C with respect to D. That's the only way I can approach this problem. V of D is 0. That's why I chose point D. Omega CD, I write it as omega CD times K. It could be negative K, but again, it is either clockwise or counterclockwise. And R of C with respect to D is this vector, which is negative 400I. In meters, negative 0.4I. Now, if you look at the two sides of this equation, this side and this side, I have two vectors equal. It means their i's are equal and their j's are equal, and I only have two unknowns, omega BC and omega CD, so I should be able to find both. If I look at the I components, I have a negative 4 here. And then I have K cross J, which is negative I. There is another negative, so it's going to be 0.4 omega BC. And here, in terms of I have nothing. So it's 0. In terms of J, I have K cross I, which is J. So I will get this one. And here I have K cross I, which is J, but there is a negative involved. So these are the two equations I get for equality of the I terms and J terms. And clearly from the top one, I can find for omega BC, it is going to be positive 10 radians per second, which means it is counterclockwise. Plug it back onto this bottom one. Your omega CD is going to be 7 divided by 0.4 or 70 divided by 4, which is 17.5, but negative, which means it is clockwise. Okay, so now I got both of my omegas, 10 and negative 17.5. So let's go ahead and replace them. This is positive 10, this is negative 17.5. Of course, radians per second, both of them. Now that I got them, it is time to look at the acceleration problem. So now we are going to attack the acceleration problem. And I repeat the same process, again starting from A, B going to B, C, and CD, and this time knowing that alpha of AB is 0, okay? So this piece of info is gonna be needed. So now I say, now A of B equals A of A plus alpha of AB cross R of B with respect to A, and then minus omega AB squared R of B with respect to A. And the reason I could do this instead of the double cross product, as you know, I told you several times, is because this is a 2D problem. Otherwise, I have to say omega cross R of B with respect to A. Now, A, again, is a pinpoint, has no acceleration. Alpha AB is 0, so that makes life easy. Omega AB was already 10 units. And R of B with respect to A, if you remember, was positive 0.4J. So if I calculate it, it is going to be negative 40J. Units meters per second squared. Okay, so that's A of B. Then I go from B to C. A of C equals A of B plus alpha BC cross R of C with respect to B, and minus omega BC squared R of C with respect to B. And again, similar to last time, I need to find A of C also to remember CD, because this first equation is not going to be enough. So it's going to be A of D plus alpha CD cross R of C with respect to D, and minus omega CD squared R of C with respect to D. Now if I go ahead and replace, A of B is already negative 40J. I found it in the previous step. Alpha BC I don't know. I just write it as alpha BC times K. Again, it's either clockwise or counterclockwise. R of C with respect to B, I found it previously. Omega BC was positive 10. And R of B with respect to C, if you remember, was negative 0.4I plus 0.7I negative 0.4J. A of D is 0, it's a pinpoint. Alpha CD I don't know, I just write it as alpha CD times K. R of C with respect to D was negative 0.4I. And omega CD was negative 17.5 squared. Okay, so now I should be able to get two equations again from here, because the i's are equal and the j's are equal. And again, if I do so, for I have k cross j, which is negative I. There is another negative, so it's going to be 0.4 alpha BC. You clearly see why I needed omegas, right? Because here I definitely need to use omegas in this formula. And if I didn't know omegas, I cannot perform this stage. And then you also will have negative 10 squared times that, so it's going to be negative 70. On the other side, we have a k cross I, which is j, and then a negative 17.5 squared times another negative. So it's going to be 0.4 times 17.5 squared. Just that. And in terms of j, I have a negative 40. And then I have k cross I, which is j. And then I have another j term here, which is negative, negative, positive, so it's going to be 40. And on this side, I have a k cross I, which is j, but there is a negative involved. So I will get this one. And again, clearly from the top one, I can find for omega BC, right? And here, if we do it, so 4 times 17.5 is squared, you get positive 481.27 radians per second squared. And that means it is counterclockwise. And plug it back down into this one, you get your alpha CD to be negative 84219 radians per second squared, which means it is clockwise. Good, so now I got my alphas. I can go ahead and replace them up there, and then I go for acceleration of the centroids G1 and G2. So two of the unknowns that I needed, alpha BC and alpha CD, are already here. These are two of those 12 unknowns. I found them, right? Okay, so here are the numbers for alphas. And now we can calculate the acceleration of the centroid for each member BC and CD. Now the question is, do I need both of them? And the answer is not really, because if we go back and look at my equations 1 to 6 and what I need to find, which are only B and C reactions, nobody here wants D reactions, then if I'm not interested in the D reactions, I can avoid equations 4 and 5 because they would give me dx and dy. So if I can skip 4 and 5, now that I know the alphas, alpha BC and alpha CD, right? These are now known. Can I look at a subset of the equations and not solve all 6 of them? Can I only look at equations 1, 2, 3, and 6? And the answer is yes. If you look, your B's and C's are showing up in 1, 2, 3, and 6. If you don't care about these, you can only solve 1, 2, 3, and 6 for B's and C's. All you need is a g1x and a g1y. So you only need to find the acceleration of g1, which is the centroid of BC. You do not need to find acceleration of g2, okay? g2 is good if you want to get into equations 4 and 5. So I do not need to find ag2, and so I can only solve for a subset. So all I need is AG1. How do I find it? Well, point G1 belongs to member BC. So I can find it by relating acceleration of it to acceleration of another point, let's say point B. So I can say this is equal to acceleration of B plus alpha BC cross R of G1 with respect to B minus omega BC squared R of G1 with respect to B, correct? And I have already calculated A of B, if you remember. A of B was negative 40J, so I can plug it in. Alpha of member BC is calculated. It is 481.25K. Omega of member BC is already calculated. That's positive 10. And R of G1 with respect to B, it goes from B to G1. So it is this guy here in black. It's the same as R of C with respect to B, but half of it. So you go half of 400 down and you go half of 700 forward. So it's 350I minus 200J, correct? Or in meters, it is 0.35I minus 0.2J. And if you plug in and calculate the cross product and the vector multiplication, you will get 6125I plus 148.44 J meters per second squared. So now those two pieces of info that you needed, which was AG1, the X component, and A of G1, the Y component, now you have them. 6125, 148.44. So now if you go into these equations, you know these two other pieces of info that you need. And now all I need is to look at equations, as I said, 1, 2, 3, and 6. Nobody needs any other equation like 4 and 5. Okay, which one do you start with? 6, because 6 has only one unknown in it. Once you know alpha CD that you do, from equation 6 you can definitely find C of Y, which will be negative 922 newtons. And now if you go and plug that into equation 2, which has only Cy and By, now the only unknown in 2 is going to be By, because Cy is now known. So I'm going to plug this into equation 2. That should give me By, and By is going to be 1238 Newton. Okay, so this is Cy, this is By. Now I plug both of these By and Cy into equation 3. Because now 3 is going to be only an equation between what? Cx and Bx. By and Cy are now known. So 3 is going to only have Bx and Cx, and 1 also only has Bx and Cx. So it's going to be, if you add it to equation 1, you will have 2 equations and 2 unknowns. And the unknowns are what? Bx and Cx, which will be negative 1959 Newton and 2081 Newton. Okay, so here all the reactions at pin B and C calculated for you. Good, so this is how you solve this involved problem. Now, before I end up this video, I want to look at one thing for you. You might say, well, okay, I did all these calculations. And guess what? All of these calculations are only valid for this moment, right? These are all momentarily instantaneous equations. When this mechanism rotates a little bit, and this member AB moves a little bit, right? So it comes here, let's say. And then member CD goes something like that, and member CDE goes something like this, and so on. All of these distances would change. And so the omegas would change, alphas and A's would change, and all of these forces would change. So you have to keep calculating all of these numbers, all of these calculations, let's say at least for one loop cycle, right? For when this member AB goes one full cycle. If you do, definitely you are going to get different numbers for B, C, and so on. If I'm interested in, let's say, the pin at location B, So the force on pin B is square root of bx squared plus what? By squared, right? So if somebody says what's the force, total force on pin B, you square these two numbers, this negative 1959 and that 1238, and that gives you the total force at B, right? And as I said, if you plot this magnitude of force B versus time or versus the angle of member AB, theta AB, for when it goes from 0 to 2 pi, you are going to get a plot, right? Let's say you get something like this. Good. And you have some maximum B in the positive direction. And you also have some minimum B in the negative direction. Now, if I give you the simple task of designing a pin for this mechanism that can rotate lots of rounds without failure, right? So you know if it's a single pin, it is subject to the shear stress, and the shear stress in this pin is going to be the total force divided by the section area, which is pi over 4 times d at pin B squared. And it has to be less than or equal the allowable shear stress. Correct? If it's a static analysis. The matter of fact is this is a dynamic load, so you cannot even do it that simple. Right? For example, if it was just a static analysis, you say now, yes, this T allowed is, for example, the T max divided by a safety factor, or you can divide this by a safety factor and say T allowed is, let's say, half of the shear modulus for a tensile material divided by safety factor. So if, for example, I choose my material for the pin, which means I know this, and I know my application allows for so much of safety factor, since I know this force B, that gives me the diameter of the pin that I need, right? So you see, if I want to calculate just a simple diameter for the pin that keeps this mechanism working without failure, I need to calculate the force B, and which B among all these different B's is going to go there? Well, probably the max between B max and B min if the material behaves the same in compression and tension. If the material behaves differently under compression and tension, you have to do this separately and then choose the minimum load or the maximum diameter between the two, correct? So this is going to be, let's say here, this B max in magnitude is less than B min, for example. Then here you have to use, let's say, B max if the material behaves the same in compression and tension. So find what is the maximum load during one full cycle by repeating these calculations over and over for so many different angles, let's say at least 360 angles. So for each 1 degree, you calculate this one more time. Find B max, choose your material, see your application allows for how much of safety factor, and then find the desired size of the pin. If you do it, what? A simple static analysis. The matter of fact is, when the material are subjected to a dynamic load like this, a phenomenon happens in material called what? It's called fatigue. And when you want to design parameters for fatigue, the matter of fact is the strength of the material is not simply going to be the yield strength or half of that for the shear stress. This guy is going to go down. In some material, the more that you apply this dynamic load, the variable load on the object, if you look at the strength versus the load or the number of cycles, so N here is the number of cycles. If you look at that, for some material, it just keeps going down until it reaches 0. For some other material like steel, it goes down until after so many rotations, now it goes to a constant level, which we call the endurance limit, SE. And then using that SE, the number of cycles and so on, you will design for your pin, which we call fatigue design. And there are different methods like Goodman and so other. There are 3-4 methods that you can use for fatigue design. Later on, when I start creating my videos on machine design, I'll talk about this. But you might wondering that a simple design of a single pin in this mechanism that works for so many cycles or for so much of time before it fails is quite a daunting task. It needs lots of dynamic calculations, good knowledge of machine design, good knowledge of the material and everything before you can design just a simple pin in this mechanism that can work, let's say, for 1,000,000 cycles, 10 million cycles, for 1 year, 2 year, and so on before it fails, or for 100 years, right? And the other stuff are like now the heat generated, there is a stress due to heat, there is lubrication. When you cut the member BC with that hole, there is another thing here called stress concentration and so on that you need to look. So when you make this diameter of the pin bigger and bigger, and you are going to add to the stress concentration inside member AB. So you cannot just choose whatever pin you want without looking at what's going to happen to member AB or BC or any other member that has the hole for this pin. You are making those weaker, right, by reducing the thickness at the hole and adding to stress concentration. So yes, choosing a simple pin, creating or designing a simple pin in a simple mechanism like this is quite a daunting task if you want to do it properly. And for that, you need to know your dynamics very well, your machine design, and so many other things, heat transfer and so on, before you can reliably select the pin. So just wanted to tell you why these calculations like this are important, right? For everything you do, calculating these dynamic loads, which are varying by time or by cycle, calculation of these are important. Typically, material would endure a lot less under this variable dynamic load than when you're just applying a constant load on them. They don't move like a truss, right? And everything is static. So hopefully this video was useful to you, and I will see you in my next lecture. Thank you.